I just wanted to say a couple of things. One is that, you know, we come here to Jerusalem as pilgrims, as many before. And to me, the reason we come as pilgrims is that the modern era of computational neuroscience, in my view, really started here. And it started when Hanok and Haim and Danny Amit really brought the power of statistical mechanics into a neuroscience problem. That's one element of our pilgrimage. The other, I think, we have to acknowledge is the ICNC, which really was one of the first centers, and this again, Haim, I guess, Moshe, Idan were big elements in this tele, you know, to bring a whole new kind of program. And then I think the third thing is what we're doing today, is starting international collaboration, hopefully in a really new and positive way. And of course, we want to thank David Sainsbury and Sarah for that. I wanted to say one more final thing. I mean, I think we all feel very proud of ourselves. These are three very, very good centers. And I was going to sort of say that we can come here today and define what an impossibly difficult problem is. It's one that we collectively can't solve. But then, as I was thinking of what to say, and I realized, well, I acknowledge Danny, and it's Danny Amit. It's very sad that Danny can't be here today to see this moment. But I think let's all keep in the back of our mind that if Danny was here, he would be goading us to do better. And so as we sit here together, we can feel proud of ourselves, but let's try to have Danny's voice saying, you know, how can we do this better? And one way is by talking to each other, finding the good problems, and solving the good problems. All right, so let me actually do something here. I want to just dive into it by considering what I think is an interesting task for building models and thinking about neuroscience problems. It's a task currently being studied by Mehrdad Jazieri and Michael Shadlin in both people and animals. And the task goes like this. Either a person or an animal is given a stimulus, could be a light flash or a click, some kind of sound or some stimulus, and then a little while later another stimulus. And the task is to respond either by an eye movement or a button push at an equal time after the second stimulus. In other words, you're supposed to match with your waiting interval here the interval that you've been cued with by the two stimuli. And of course, the stimuli come at different intervals during the task, and you have to adjust your response appropriately to do that matching. Okay? So this is obviously an interesting task if you're interested in how time is measured, how time is stored, how time is estimated in neural systems. And if I had given this talk, I think probably in the first couple of meetings before the Jerusalem people showed up, I would have sort of thought of it this way. I would have said, well, we need some kind of mechanism in order to be able to estimate that time interval, and I would have thought really hard about possible ways that a neural circuit could estimate that time interval. That time interval then has to be remembered somehow, so I would start thinking about memory storage issues. Then the second time interval has to be estimated before the response. We need to do some kind of comparison, I guess, and when the neural circuit concludes that the two time intervals are the same, go ahead and generate the response. And I think I sort of would have followed a rational, at least as rational as I can be, approach to this problem, thinking of these mechanisms, and then trying to hand build a neural circuit that would do those different functions. But I want to present to you today a sort of intelligence-free way of building such a model. Now, it's intelligence-free for two reasons. One, you'll see, but the other is that I work with David Cicillo, so my intelligence does not have to be engaged because David does everything wonderfully and very intelligently. But nevertheless, I think you'll see what I say about intelligence-free. So here's a way to construct a model like this in 2 minutes, maybe 3 minutes if you're having a bad day. And it goes like this. You start off with a generic neural circuit. The circuits that I'm going to talk about at the beginning of the talk, the balls here are going to be firing rate models. I'll give you the equations in just 1 second. But later on, they're going to be spiking networks in here. But for now, they're just rate models. It's hooked up in a random way. You start with a generic neural circuit that hopefully you already have on your computer, so you don't have to do that. And it's not in my 3-minute estimate. It's not included building this generic model because you're supposed to have it already. Okay, so here's the nature of that model. As I mentioned, it's a standard firing rate model. X is an activation variable. It decays to 0, except that through synaptic input, it's being constantly regenerated. The firing rate is given by some nonlinearity. Often it's a hyperbolic tangent. If the negativity of this bothers you, we can use functions that aren't negative. And obviously, when we build spiking models, we won't have negative rates. But at any rate, some nonlinear function like this. And this network by itself is constructed completely randomly. Now, what does random mean? Random, among theorists, you can use that word. My advice to you is never use that word in front of an experimentalist, however, because it seems to do bad things to them. So what does random mean? Random really in this context means it's not designed specifically for this task. It's designed to be, I would say, your best model of what you think, for example, a cortical circuit might look like, which isn't random, presumably, but not built specifically for the task. That's what I mean by random. Oh, but of course, among us, I can tell you we really do construct it randomly, which is we take J from a Gaussian distribution in this case with 0 mean. That's the idea that this is a balanced network. And with a variance scaled like 1 over the number of synapses. This is the standard balanced, Carl van Vrieswijk and Chaim Polinski type of network, although in the rate version. Okay, and so this model by itself doesn't do much of anything. The way we configure it, and again, as Chaim and collaborators found many years ago, it just exhibits chaotic fluctuations. And so what do we have to do to make it do a task? I mean, right now it's just kind of a fun network. So first of all, we've got to get the input in. Remember the task. The task is that we're going to give 2 stimuli with a specific time interval between them, and then vary that time interval. So obviously we just need to introduce some inputs into this network, and we do that in the same spirit. Namely, we're going to introduce a couple of input pulses as input currents to these neurons, and they're going to go in through, again, random synaptic strengths. Again, just chosen from the same distribution as these guys, although stronger, so that this one input can have an effect. If you want, this is actually representing multiple synapses. But the same idea. So we've got our input in, and then obviously we're going to have to get an output out of this network to be the response that we're talking about. We need some bump or something. It doesn't really matter right now what the response is. We just want the network to be able to tell us, okay, the time is up and I'm pushing the button. And we're not going to build a button pushing network, we're just going to build a pulse. So how do you get a pulse out of this network? Rather than take it out of any one unit, we follow, again, sort of standard neural network ideas and build a linear readout unit from the many so that we can sort of have the network collectively make its decision. We're going to sum these firing rates through synapses with what will turn out to be adjustable weights. And then we want this network to pulse this out at the appropriate time after this input. Then it will have achieved the task. If you try to do this, you will fail. But the trick for pulling this off was introduced by Jaeger and Haas, which was to take the output of the network, which ultimately we're hoping is this pulse, and feed it back into the system. And I'll come back later to why this is a very good idea. I hope I will if I have time. And again, that feedback comes through random synapses. So these synapses, again, they're quite strong because there's only one input coming back here, whereas there are, in our network, something like 100 inputs coming from other guys. So these are strong synapses, and I'll come back to that later. But coming back into the network so that the thing forms a closed system. And then what Jaeger and Haas showed, and then I think David and I improved upon a bit, is a learning algorithm, which I might get to at the end of the talk, but for now you'll just have to take it on faith, for adjusting these synapses and these synapses alone and getting this network to do something interesting. And what I'm about to do now is to show you a whole bunch of examples, including this timing example, in which networks like this, the networks always have 1,000 units. They have about 100 connections. I think they have 100 connections per neuron. And they're just constructed like this. And the key is that everything inside the box is random. Again, random in the sense both of really being random when we build it, but of being unrelated to the task. The only task-specific parameters, if you want here, are these weights, which are adjusted to make the task work. So if you have one of these networks on your computer, which we do, and you want to do a new task like this, all you got to do is program the inputs on, apply the learning rule, and literally in a couple of minutes, out will come the task. And this task is very successfully done by these networks. So here's an example of the input and the output of the network. And I'll show you a bit more, but the idea is here, the inputs, they're coming at variable times. We do them with a plus and minus 50% variability on that time interval, just like in the experiments. And, you know, sure enough, the response comes at an equal time after. And this thing really essentially does this task perfectly. You know, I can give you a bunch of examples. So, and it learns it in about 30 or 50 trials. So these trials come at random times. One is that, like monkeys, these networks will learn anything you give them. And so if you produce trials in a periodic pattern, they will learn that pattern. And you don't want them to. You just want these networks to respond to these. So these occur at random times, random time interval between the things, and the thing works. So somebody have a question? Okay. So it works. And as I say, it takes about 30 or 50 trials for it to figure out how to do this. Now, what's interesting to do now, since you've built a network without a plan, which is very unusual to me, makes me kind of uneasy, it really kind of puts you on the same footing as the experimentalists, namely you don't know what the hell you're doing. So you can start looking at the firing rates within this network that is doing this task. And I like to say that every line here is a science paper, or every other line, and the other ones are nature papers, because I could tell you great stories about these. You know, there are, like here's a guy who kind of responds to the inputs but not to the output. Here's a guy who's inhibited by the output. Here's a guy that responds to both. You know, that I can tell you story after story. But basically, I don't have the faintest idea how this network works. It's an unusual, I mean, you should think about it a little bit. I have another, maybe a little more illuminating slide with less on it. What's happening here is that you're setting up a pattern of activity through these pulses. I mean, you can obviously, these blips are due to the input pulses. That results in a sort of instability in the network that's driven through the feedback loop. And that instability drives this output pulse. But why that instability in this case takes, you know, this much time to grow, and in this case takes this much time to grow, etc., is really at this point a mystery. It's a solvable mystery because we have complete access to these models. But I'll come back to this in a while. But what I like about these models actually is that it does put you on the same footing as an experimentalist. But you can answer the question, unlike, you know, you can definitively answer the question. This is a deterministic model with equations that, you know, there's no magic here. Here's an example of that. This is actually a model. As you can see, there's noise on this model. And one of the questions in your mind might be, how noise resistant is this network? I will get to that. Here's a case where there is obviously noise. This network has successfully done the task. But I just wanted to show you, in this case, what happens after the task is over. This thing goes into oscillation. So there's another Science and Nature paper about how these oscillations are the essence of how the timing is done. Completely wrong, right? That's not true. So that's the idea. In these models, we can find out which phenomena, like these oscillations, actually have nothing to do with the way the task is performed, and which actually do. That's the idea.
So the bottom trace, I don't know if it's science or nature, but is it one of the units, or is it the output?
No, this is one of the units. This guy's not oscillating. Yeah, and this guy's not really oscillating.
So this is Dr. Job, this unit.
This what?
Yeah, I mean, you compare it to the response.
Yeah, this one is very like the response. I don't know why. I mean, the response is not being read out of this unit. It just happens to be that way. Yeah, so I don't know. Would you accept it to Nature and Science? Okay. I'll show you just a bunch of tasks that this network will do and then get on with it. This is a delayed match to sample kind of task. In other words, this network is supposed to respond whenever there are two big bumps or two little bumps, but not a big and a little. So only when the two things respond, it does it. Again, it's very unclear from looking at the traces why it is that this pattern of activity generates a bump, and this pattern of activity, I've kind of cut it off here, but it didn't generate a bump. Why doesn't this generate a bump, yet this did? But I'll come back to how we would get to that. I'm going to bore you with this, but you know, we're sort of delighted with ourselves, so I can't help it. Here's a network that responds only to double pulses, not to single pulses. So again, there's something about the double pulse that triggers this instability, but the single pulse doesn't. Again, you can write your Nature and Science papers about those firing rates. Here's what we call a sort of a Romo-like task. In this case, we've just grouped it so all the responses are on the top and all the non-responses are on the bottom. They're actually random. But the idea is respond whenever the first pulse is bigger than the second pulse. But they're randomly chosen in height. And don't respond when it's the other way. And you know, these are completely random. And the only time it fails, of course, is when randomly you choose these and they're very close to each other. It can fail. But you know, it's a very complicated rule you've imposed here. Yet something about these patterns of activity does not trigger the instability, and something about those does. Yeah.
So how does the supervision work here? What's the supervision?
So in the supervision, what do we do during learning, in other words? What we do in learning is we obviously put in an input like this, and we put this in as the desired response. So we put in the answer. We train it for a while and build it. And I just want to say, maybe I'll come back to it, but I'm not trying to argue that our learning procedure is a learning procedure that you would want to say is occurring in the brain. This is a way of building networks that do interesting tasks. So I would say in the end that the network we build takes seriously, but the learning algorithm, for the moment, you don't have to take. Here's an example where you get a fairly complex response from a pulse. It's just a triggered pulse response. This is done in response to Mark Churchland and Krishna Shenoy's work.
Wait, so can you go back?
Yeah.
So the output here, this is the desired output?
This is actually the desired output. It was just to get a complex waveform. So yes, exactly. This shape is what you want. What the system was asked to do. Just, you know, it's just a sum of some. Huh?
This is not motivated by something.
Well, it will be in a second. This is just made up. Yes, that's right. And then here's a delayed response. So the idea is how long can you postpone these stabilities. So this is about a second. The only time constant in these networks is 10 milliseconds. So you can get something like a 1 second delay before your response. And I think mercifully, I'm almost done. Here is an example where the network outputs this complex wiggle if you give it a big pulse, but a different response if you give it a little pulse. You can see the network's having a little trouble doing this. This is a hard task. These inputs only differ in their amplitude. They don't differ in their pattern. That bothered Mark Churchland. He wanted a more linear looking network, so we produced a more linear network. In this case, the height of the pulse is proportional to the height of the response instead of getting very different ones. Okay, anyway, smorgasbord. Now, here's a case where it's actually motivated by experiment. Those are just a bunch of fun examples. These are experiments done by Mark Churchland, Krishna Shenoy, and collaborators in which a monkey is cued to reach to a target and then reaches to the target, and they record. There are 3 kinds of recordings here. I'll show you on the next one. Relevant to us, recordings in premotor cortex, recordings in primary motor cortex, and recordings of the muscles, of the activity in the muscles. So this is, again, an exercise in building these kinds of models. These are the actual recordings on the top. There are 27 of these mashed on top of each other. These are recordings just from different cells, and there are actually 8 of these. So they recorded from 8 muscles, but I've thinned it out so you can see what's going on. So these are the EMGs. This dot is when the target appeared, and this dot is when the motion was initiated by the monkey. So you can see some preliminary motor action, and then here the arm is actually moving. So what David did here was to take this as input to one of these models, stick it in, and then train the network to match these EMG recordings. And as you can see, they match very well. And this was literally hundreds of these were matched, because I've only shown you 3 out of 8, and then only 1 of the trials. So there are trials for different directions, different speeds. So a single network was able, on the basis of this, to match these extremely well. And now the question is, when you build such a model, you feel kind of good, then what do you do? And really, I want to stop for a second and talk about that. Here we did the most natural knee-jerk thing, which we took some of the activities. These are really recorded activities. These are activities recorded from our network, and you can just look at them and compare them. It's not a particularly good thing to do because there's an incredible heterogeneity here, there's incredible heterogeneity here, and if you want to mix and match, you can probably do it. The only lesson here is that you might notice this looks lower frequency sort of than that, and I'll come back to that, but I believe that's because these are rate models and these presumably are not rate models, but actual neurons. So you know, there's some systematic things, but I think that's my next slide. Yeah.
So the input is the pre-motor recording?
These recordings were the input to one of these networks.
And
it was trained to produce this.
And where do you read out the motor? No, the middle one.
Yeah. So then you go in and you look at your rate, the rate
just a
network. This is just a random sampling of those, right? So again, you know, I don't know what to make of this match. And I think the challenge here, again, is what do you do? I'm going to throw this out as a question with a little bit of suggestions, but you know, what do you, when you model this way, what on earth are you actually doing? So let me contrast it. Normally, you know, we have a task that an animal does, like these reaching tasks. We have a bunch of data, and again, you know, what I think I would have done in the past is what I would have tried to guess a mechanism. How is the animal measuring time intervals? Maybe there's ramping neural activity, who knows? And then, you know, build a model, a neural-like model on the basis of that idea, and then at this point compare, you know, activity in the model and activity in the data, and then hope to say, okay, you know, it looks similar, so therefore I've established that the mechanism I made up is actually applicable to this experiment and to this data. I'm kind of disenchanted with that method, mostly because I don't think we're going to get it right. I think we're too clever to get the right answer here. We will make nice, optimal, clever mechanisms to explain the data, and nature won't. So I don't have much faith in this actually working. And so the problem here is much more to say, take a task, get a model to do it in sort of in parallel with the data, like I have. And you don't have a mechanism in mind. It's a complete unbiased thing. And then really the question you want to say is, what methods would I apply to extract the mechanism from both of these things? You're sort of left with a much more parallel situation. Of course, you have much more access here, so that you ought to be able to pull out from this what you mean by mechanism than you do here. And the idea is that the methods you use to get from here to here hopefully can be applied to the data. And so the match is made sort of at this level, not at this level, not by comparing one of your neurons to one of their neurons, which I don't think is really going to be a very, very definitive. And so that's what we do. For example, various linear readouts, not the linear readout we're doing, but linear readouts, for example, to try to extract a timing signal or an elapsed time signal. Unlike that, you know, we haven't done this yet, but try to make these work in the model, and then they tend to be things that you can apply equally well to the data. So the idea would be that you extract this pathway through a more parallel route than imposing a mechanism. Okay, so the biggest complaint that I would have if I was sitting out where you are sitting is that these are rate models, and they're doing pretty sensitive tasks. What about noise, and in particular, what about spiking, which is a hell of a noisy way to tell somebody how fast you're firing? So what happens in these models, which right now the output of any one of these things is a continuous function, which is what we call the rate, and then which gets sent to the others. Neurons don't have that luxury, of course, of sending continuous variables to each other. They send spike sequences to each other. So what happens if you replace these units by spiking units, okay? Now, you might do something like what I just showed and say, okay, I'm just going to take every one of these rate units and replace it by, let's say, an integrate and fire model, in which case now the output of this guy will be like that. But I might, you know, in anticipating that that's going to be kind of a noisy way to live, say that maybe these rate units are clusters of neurons. And so really the output of this blob is, you know, 100 integrate and fire models or something like that, and is this collective spike train, which gets sent through multiple axons to this next unit. So I'm going to keep that in mind. And a quick starting way to do this is not where I'm going to end up, but it was actually quite informative, was done by Brian De Pasquale, who, as a rotation project, is to take your rate model and just replace the transmission of the rate by spikes. So the idea is here, it's the same model as before. A rate is computed here from some nonlinear function with the same equations I showed you. But instead of transmitting that real number along this thing, at this point, you take the rate that you've computed, normalize it by some maximum rate, which I'll talk about in a second, and actually send spikes generated by a Poisson process down this line. At this point, they're integrated through a synapse with a 10 millisecond or something, a few millisecond time constant. They go into here, and you go back to your rate model. So it's just a spiking transmission model, hybrid model. And the parameter here is what's this R max, which you can think of as the maximum rate for any one neuron. We take that to be the 100 hertz, times the number of neurons that you think are inside this blob. So it's just a way of estimating how many neurons it's going to take to make this work. Okay? Make sense? And it's just a cheap and quick way. So the quantity we're going to calculate is the autocorrelation function of the rates. And again, we have the rates in this model because it's a hybrid model. Averaged over the system. Again, this is something that Heim and collaborators made great use of for rate models like this. And in fact, one of the things they showed was that this correlation function drops in a kind of a funny way and slowly. It's sort of a Gaussian shape, not the kind of exponential shape that we often associated with correlation functions like this. And it falls fairly slowly. So here is the average autocorrelation function rate model. If you replace each rate model by one spiking model, what you find is much more the standard exponentially decaying thing. And that's because of a phase transition, which in discrete models was worked out by these guys, and an analogous transition was worked out in collaboration with Heim. A phase transition that occurs due to the noise, essentially. The noise of the spiking here is destructive to the slow chaotic dynamics that's giving you this correlation function. So this kind of kills the model, and I guess I'd skip this, but the reason that these models work, in particular in doing relatively slow tasks, is because of this large, relatively long time correlations that exist in these rate models. So this kind of kills things. Now, you can slowly crank up the number of units, the number of spiking neurons that correspond to each rate unit. And when you get to about 1,000, you're on the other side of the phase transition. So the phase transition here, where the noise of the spiking destroys the chaos, is occurring, somewhere in between 100 and 1,000. So this gives you the order of magnitude where you're going to be if you want to take advantage of this. Now, just to show you this in action, here's a model where we don't have any inputs, where we do it one-to-one. So it's not impossible to train these networks. So, yeah. Yeah, I mean, that was just this Poisson model. I will get to real neurons that are coupled in a second, but absolutely. This was just to get an order of magnitude. And you could imagine you could do better, and you could imagine you could do worse. Okay, so here is an example, though, of a network of 1,000 integrate and fire models built just like the other networks that I showed you, but now spiking models. So they can do something which isn't too impressive, but we just asked this network to output a sine wave. And it does it. It's not a very slow sine wave. This is an easy task. This is about all this network can do. It's kind of interesting in that although it's a periodic output, for example, this spike train is not periodic. So you can do something this way, but you can't do a whole lot. And in particular, if you try to get a network to do this sort of task, one of these Poisson rate networks, to do this timing task that I showed you, here's the output. It's not very good performance. It's a bad monkey. And of course, that's because the rates you're extracting here are just ridiculous. So here it is, we're cranking up the number of neurons per rate unit. When you get to 100, it performs poorly, I would say, but kind of. When you get to 1,000, it's pretty good, but it makes some mistakes. When you get to 5,000, it's flawless. So in these Poisson models with 5,000 spiking neurons per rate neuron, which is 5 million neurons, if you really built this thing, which we're about to do, you can get this task performed perfectly. So that's a lot of neurons. It's not a particularly clever way to do it, but this is a hard task, right? So actually, yeah.
This might be a failure of your algorithm, right?
It could be a failure of many things. You mean that it takes so many?
No, yeah, it could be that there is a solution, but you just don't find it.
I doubt it. I think it is really the noise, that there's a certain noise sensitivity. After all, you remember what we're doing here is triggering instability, right? And if it gets triggered by noise. One thing you might notice, the most common error is doing something spontaneously rather than in response to the stimulus. That really is the noise triggering the instability. And you might imagine mechanisms to suppress that. For example, I know that if you don't show me a stimulus, I'm not supposed to push the button, no matter, even if some system tells me to. That's the most common error, this kind of spontaneous response, which I think is just the noise triggering the instability. Yeah?
How good is the monkey?
How good is the monkey? So,
Are you trying to model something better than
yeah.
you can actually perform?
Yeah. I think that's a very good question, because these kinds of errors, I mean, that's kind of what I was getting at. These kind of errors, even if the monkey doesn't do this, are sort of probably internally, like you sort of say, oh, I feel like pushing the button. I shouldn't push the button. The task hasn't started. That kind of thing. You could downstream edit out these sorts of responses. The monkeys, though, are very good at this task. I mean, I don't have the numbers in my head, but they're very good at it. And people are very good at it. So, yeah, I don't know how good we have to be. It's a good point. All right, so then David has built, we wanted to show that we could do this. I mean, we were really worried if we had built these beautiful models that cannot be realized with spiking neurons. And so just to convince ourselves they could, we built really a huge model that does this task. The model, as you saw from this, if you really want to do well, you probably need something like 5,000 neurons per rate model. So the idea is to take the old network, which had 1,000 neurons, and I think I have it over in the corner here. The old network had 1,000 rate units. I shouldn't really call them neurons now. We've now in a situation where we have 10 connections per unit. We cut it down a little bit, but the rate model can perfectly well do this task with these parameters. And now inside the rate model, we put 5,000 integrated fire neurons now connected. So now we're not going to cheat anymore. These are not Poisson units. They're integrated fire models connected in one of these balanced networks, like the kind of work that Nicola Brunel, Carl, and Heim have done, the classic balanced integrated fire neuron. I should advertise a little bit that this is a lot of work, and that Evan Schaefer is going to give a talk at this meeting about how to describe such an ensemble in a much more compact way. That's clearly what we would like to be able to do, but this is just brute force.
So you have 10 units like this?
We have 1,000 units like this. Little n is the number of connections between the units. So in other words, this collection, I'll say it now, this collection of 5,000 neurons sends 100 like axons to that guy, and then does that to 10 other ones.
To each one of that guy. To each one of
100 to each one of 10. So each of these 5,000 unit things connects to 10 other guys.
But within the 100 axons to that group of 5,000, is it random? What those?
Where do they go? Yeah. It's random where they go. Yes. Sorry.
And where do they come from? Among the 5,000?
Random. Just some of them. Okay? And then some of them go elsewhere. Anyway, I'll skip this because I'm running out of time. This guy does the task. Okay? So here is the output. Again, the output is obtained by taking all these spikes, integrating them through synapse-like constants. So you do get a real number for the output. Anyway, you can get this thing to do the task. It's sort of brute force. It's a proof of principle, and we are working very hard to try to do this in a more compact sort of way. So who's the boss? What do I have for time?
How much do you need?
No, you ask me.
5 minutes.
5 minutes, okay, good. I'll talk about this because it's next. I was trying to think what to do. Okay, so the issue, we have an issue of range here that in real neural circuits. I've gone from a sort of a phenomenological description of groups of neurons, that's the rate model. I've gone down by saying, okay, inside the rate model, we're going to integrate and fire units. I want to now go up and say, what if you started thinking of networks of networks? Because the idea is that we want to be able to show these networks can do impressive things, but they're obviously limited. But if you could build networks of networks that sort of square the capacity, you're really lengthening time constants, right? We start off with a 10 millisecond time constant. When we build a network, we can do things out to about a second. The question is, that's an improvement of about a factor of 100. The question is, if we built networks of networks, could we go out to 100 seconds? If we could go out to 100 seconds, we would be very happy. So how do you go to networks of networks? And I want to do this because I want to throw this out and then have people, you can feel free to come up to me after or during the meeting and tell me that I'm stupid or that you have a better idea. So here's the idea. We're not gonna build the integrate and fire models in this case. This guy is supposed to represent one of the rate networks that I start with, but we want to build networks of networks. So in this case, what we want is a much more compact description now of the network I started with, because we don't want to have to build millions of these rate models. So what I'm going after now, what I want to present to you is ideas about how to describe a model like this more compactly, so that we can start ramping it up. So this model, if it has, it has this equation plus it has some nonlinear relationship. If it's fully connected, it has n squared equations, where n is the number of neurons. If it has n connections per neuron, it has n times n. So there are n times n of these equations you got to deal with. But what you find, and this also came out in the work that Kanika, Rajan, and I did with Haim, is that in most of these tasks, the actual activity that you see, either in terms of the x variable or the r variable, is in a much lower dimension. So you can do a principal component analysis of x or of r, actually and of r. You can derive principal component eigenvectors, and then expand these activities in a much smaller number of dimensions. Often, S can be 10 or 20, even though n is 1,000. So because this equation by itself is linear in both x and r, it's trivial then to change this equation, just as you would do in a linear equation, to a much smaller set of equations, now something that can be done in s squared operations that describe these, sort of transformed variables. So if this was the whole story, you'd be happy. But of course, it's a nonlinear model. It's not the whole story. You have to deal with this equation, which is this equation, right? This is your expression for r over here. This is your expression for s. And this is, of course, where things get tricky, because this is nonlinear. Now, you can think of this equation. This equation is for every I. So these are n equations for s unknowns. The idea is that x comes out of this equation, and then you put your x in there, but you have to extract what you think these r twiddles are. There are s of them. So this is n equations for s variables. That's overdetermined, right? And the idea is that can't you extract those s variables from a smaller number of equations? The answer, now you might think, why can't s variables, why don't I need just s equations and then I'm in business? That is not true. That's definitely not true. And the reason is that there are instabilities that set in. I don't have much time to go into this in detail, but if you just try to extract, you take s of these equations and extract your s variables, you'll get the right numbers for these variables. But the little errors that you introduce will go through this system, through this equation, through this transformation, be unstable and blow you up. So what we're analyzing now is where in this range between n, where this would be perfect. If you allowed yourself using of all n equations here, no problem. This thing works great. If you use S, we know it doesn't work. Where in that range are you? And we have evidence and belief that this only weakly depends on n. But I wouldn't guarantee it at this moment. So the idea is that ultimately we replace this n squared or n by n system with an n by s system where m is less than n, perhaps considerably, and s is less than n, perhaps considerably. Furthermore, there's a technical thing why these models run incredibly faster than these, and that is that performing sparse calculations, in this case, on a computer is just much less efficient than performing full matrix calculations. So we really get a big speed up. And just to show you that this works, here's an example of one of these networks producing a fairly complex output. And this is actually two models. And every line you see is two lines, but you can't tell the difference because they're identical. So this is a full-size 1,000 network with 100 connections and a reduced model with 45 components being computed and this m variable being 330. So you know, it's completely indistinguishable at this level. Okay, so that's anyway the program to try to get through this range of going from neurons to clusters of neurons to networks of networks to see really what is the capacity that you get from this full range. And the tricks that we're going to need, one is that Evan's going to talk about a better description of spiking networks, hopefully, so we don't really have to model every integrate and fire cell, and then perhaps a compactified representation of even a rate model network, mechanisms to try to get us through this range. All right, I will stop there. Exactly right. They're random within here. If you looked at this and you replace these by dots, it would look random. But if you actually look at what that projection is, it's actually a low rank projection, which is trying to pull out. Typically, we want to go to longer time scales. So what we try to do is pull out the slowest principal component about here and transmit it to the other guy. So you're exactly right that on different scales, they look like low rank matrices, random matrices, low rank matrices.
Is there any evidence whatsoever?
Yeah. Yeah, so, you know, this is obviously your connectome claim.
No claim.
Yeah, no, yours. I said it was yours because I don't have enough guts. How would you see such a thing? I don't know. We're thinking about it. It's obviously not so easy.
Do the time constants change between the networks?
Say it again, sorry.
Do the time constants change between the networks, the levels of the networks? So it's all,
that's the hope. That's exactly the hope, that the effective...
When you create a network, like the tau...
No, we leave the tau the same. Yeah, the idea we leave the same. Bitter.
So we know there are some dimensions of noise which really are expressed in time. So, but they're not instability noise, so they would drive the instability for long response. So can you get like proper like scalar noise and timing, but still have enough regularity that then generate sort of bad extra responses?
Yeah, I mean, you don't want to be perfect. You don't...
Exactly. You don't
Yeah.
want the instability to cause bad responses. You want bad causing bad timing.
Yeah. Yeah, so I think getting occasional spontaneous responses out of the blue, we won't be able to get rid of completely. And I'm not sure I'm so worried, again, because I think you could have downstream filtering and just say, I'm not supposed to push the button. the quality of errors, the way humans and monkeys do, they cheat at the ends. They tend to be short on the long intervals and long on the short intervals. And these things fail in that way. So the pattern of failure is right. What we don't know yet is, for example, did the error scale with the time interval? We just don't know that yet. Yes, we would like to get that right. Okay?
Just a quick question, just to understand the agenda. So suppose you get a network that does very well relative to this monkey. What is the next steps? And then you understand the network. Will you have some, because you mentioned comparing mechanisms.
So what, yeah, right.
How will you use the network in order to understand?
So what I would love to be able to do, we haven't done it, is to say, if you do the following kinds of projections, it's extremely insightful. It tells you really, interesting things about how the network works. If you do the following kinds of projections, it tells you useless garbage that looks pretty. For example, nice little trajectories in low-dimensional spaces that are useless, maybe. And then apply those methods to the data. The program is really to develop mechanisms that you know are instructive in the model, and then apply them to data and hope they would be instructive. Yeah.
Of course, one thing you've already done is say that you need the feedback.
Right. We need the feedback.
That aspect of the mechanism you've already found is a required aspect in order to.
Yes, it is a required aspect. Yeah, that's correct. Okay.